When we're given a data set, we often want to describe what percentage of the data falls within a certain number of standard deviations of the mean. So maybe I want to be able to say with confidence that 75% of my data lies between blank and blank standard deviations of the mean. So we might have a variety of distributions, and maybe that distribution has kind of this bimodal shape, modal meaning that it just has two most frequent points. We don't really necessarily have a specific rule for how the data has to show up. So Chebyshev's rule allows us to make some statements. It says that at least 3/4 of the scores in your data set fall within 2 standard deviations of the mean. So within the interval x bar minus 2 times the standard deviation and x bar plus 2 times the standard deviation. That's for samples, or if we're dealing with populations, then we just replace x bar and s with mu and sigma. So it doesn't matter what the data set looks like, whether when we plot the distribution, it could look like look like this. It could be skewed. The shapes could be trimodal. It doesn't really matter what the shape of your data values is. So here are your scores, and here's your frequency, your probability, how frequently those scores occur. And we are guaranteed that at least 3/4 of the score, if that's the mean right here of our probability distribution, then subtracting 2 standard deviations and adding 2 standard deviations, we can guarantee that 3/4 of our data values will be captured within that interval. So as an example, let's say I told you nothing else but that I have collected data on heights of all people in a town, and I found out that they are on average 65 inches tall with a standard deviation of let's say 7 inches. Well, if I want to describe 3/4 of the people in my population, what I can do is look at this interval mu minus 2 times sigma and 65 plus 2 times sigma. That's going to give me 51 to 70, 79. So there's some tall people in this population, but we can be certain that 3/4 or 75% of people are between 51 inches and 79 inches tall. Now maybe we're not satisfied with that. Maybe we want to get a higher proportion of our population. Maybe we want to describe 8/9 of our population. That's kind of a strange fraction to want to think about, but because of how Chebyshev's rule works, there's a formula for this. So if you wanted to know 8/9, which is roughly speaking just over 90%, then you would look at people within 3 standard deviations of your mean. So in that case, it would be 65 minus 3 times 7 and 65 plus 3 times 7. And then we could say that whatever 8/9 is, 92%, let's say, of people fall between 3 standard deviations of that mean. So that's captured here in this picture. We can see this is for a sample, but same kind of idea. It's just sample means we've not considered everybody in the population, but we have some collection of data. And in general, the rule states this. It says that at least 1 minus 1 over k squared of scores fall within k standard deviations of the mean. So if you wanted to figure out, for example, you could solve for k here. If you wanted to describe 99% of all people, then you could set this equal to 0.99 and figure out how many standard deviations that would require. But this is kind of just a quick rule of thumb that tells you that for any data set, really the key takeaway here is that you pretty much capture all of your data values within 3 standard deviations. Within 4 standard deviations, we're talking 15/16, which is very, very close to 100%. But you can get as close as you want. Now, this is for any distribution, any shape distribution. It does not matter what that shape looks like, whether it's trimodal, like we have here, 3 peaks, whether it's 1 peak and it's kind of skewed to the right, or we have 2 modes. This works for any shape distribution, which of course means it's fairly lackluster. It doesn't give us a high level of accuracy. If we can determine, or we know that the shape of the distribution is symmetric, then we can do even better. And here's how we can do better. It's called the empirical rule. And the empirical rule is kind of the same idea. It says that for a set of data whose frequency distribution is bell-shaped and symmetric, okay, bell-shaped, you can kind of imagine what a bell looks like, and if it's symmetric as well. So here, this one is not bell-shaped, right? This is kind of our bimodal one. This one's not symmetric because we see that here it kind of picks up and then here it kind of just drops off. And so that's not symmetric, and it looks like there's a little bit of a skew on that. And here's a bell-shaped symmetric distribution, so it has the shape of a bell, and we can see that if we cut it down the middle and fold it in half, we would have symmetry. So this does a little bit better in that this can guarantee that, notice, we can actually describe 1 standard deviation, and 1 standard deviation, 68% of our scores will fall within 1 standard deviation. Doesn't matter whether we're talking population or sample. Remember, sample just means that it's a subset of the population. Population means it's everybody being considered. Now, this is why I said it does 1 better, because we can say that within 2 standard deviations, remember back up here, when we didn't concern ourselves with the shape of the distribution, 2 standard deviations only captured 3/4 of the scores. But if you know that your distribution is bell-shaped and symmetric, then you can guarantee that 95% of your values lie within 2 standard deviations. So if we look at another instance, maybe we look at some exam score, and maybe the exam average is 80%, with a standard deviation for, let's say this is an entire class, so we'll treat this as a population. Maybe this is a 6% standard deviation. So we could say that in this case, mu minus 2 times sigma and mu plus 2 times sigma. This will give us 68 and 92. So 95% of all scores, or maybe these are exam scores, fall between 68% and 92%. Notice that I didn't need to provide you with the data. All I need to really tell you is that this comes from a symmetric bell-shaped distribution. You don't actually need to see the values. However, if I gave you a data set and had you compute the mean and standard deviation, these rules would still apply. You could still guarantee these truths, which is really cool, that regardless of the shape of your distribution, no matter how messy that distribution is, you can still make some guarantees about your data values in your data set. So no matter if I give you, say, 10 data points, and we can't verify that the distribution of those 10 data points is symmetric and bell-shaped, then you can still guarantee that 3/4 of those values will be within 2 standard deviations of the mean, which is pretty neat. So Chebyshev's rule, this is when you can't make any assumptions about your distribution shape. However, if we're told or we can determine that our distribution shape is symmetric and bell-curved or bell-shaped, then we can be more confident of the data points that lie within 2 standard deviations. And that's kind of the key idea here is if you know the shape of it and it's bell-shaped and symmetric, then you can make observations with stronger confidence. If you can't assume the shape, then you can only determine that 75% of your scores fall within 2 standard deviations, which is still pretty good, but 95% is considerably better. And for 3 standard deviations, it's 99.7%. And for 3 standard deviations here, it's 8/9, which is actually like 91, 92%.